Our first talk will be by Krste Asanović. He's Chief Architect at RISC-V International, and he will talk about the topic RISC-V State of the Union. Welcome.
Okay, hello everybody. It's great to be back at an in-person summit again. I tried to go to the one in November, but then unfortunately got COVID, and so couldn't be with you last time. So today, there's a bunch of themes I want to go over. I'll be representing RISC-V International, the technical side, in my role as Chief Architect there. Tell you what's been happening, where we're going, what directions in terms of the architecture. One of the things to realize is we've only got this far in RISC-V because of the community, and so people working together. And I just want to remind people, at these events like this in person is where we made a lot of progress on technical ideas, technical standards. So I'm going to be talking about a bunch of things, including stuff where there's open issues, just to kind of seed conversations. So while you're here over the rest of the week, find your colleagues out who are interested in these areas, and let's try and have some discussions while we're here. So I'm here to talk about the State of the Union. So what I'll say is the State of the Union is strong, right? So it's amazing. It's amazing where we got to in RISC-V. So looking back, it was about 10 years ago when we all ran around hot chips wearing these T-shirts telling people you should go use RISC-V. And at this point in time, what you see is RISC-V is solidly established in the embedded space. So you will no longer get fired for choosing RISC-V and putting it in your SoC. It's a sensible, everyday decision to include RISC-V in the embedded space. And if you saw the numbers Krste was showing, it's predicted that's going to just go up and to the right. So very solidly in the embedded space, no reason not to use RISC-V in a lot of those sockets right now. Now, what you're seeing and really exciting is it's on the verge of widespread adoption in application processors. Now, in the embedded space, historically, there's been many, many instruction sets in that space. It's much easier in the embedded space to introduce something new and original because quite a limited software impact, right? Though even in that space, what you see is a consolidation of all those different embedded processor ISAs. All those companies who had their own ISA are now switching to RISC-V almost universally as a common open standard to help with software tooling. In the application processor space, it's much, much, much more difficult to come in with a new ISA in that space because of the incredible variety of software you have to get working. But even despite this, RISC-V, basically there's only x86 and ARM competing in this space right now. And now RISC-V is this new entrant, and this is a big challenge, but what we're seeing is a lot of interest here, development of both the high-performance processors and the software ecosystem starting to come along with that. This will take some time, but we're really on this verge of widespread adoption of RISC-V app cores. And I think you'll look back, 5 years' time, we'll look back and say, I can't believe it happened this fast, right? That's really how things are going to go. AI. So you cannot give a talk these days in the computing industry without mentioning, in fact, in any industry, without mentioning AI. What's interesting is RISC-V is the standard core in people building new AI accelerators. And there's a bunch of reasons for that I'll get to a bit later in the talk. So the State of the Union is strong, very solidly established in embedded, coming to you soon in application processors. AI, we've been there already in a lot of the products out there. Now, one of the challenges of RISC-V people like to bring up is this problem with RISC-V, is it a flexible ISA? Is it rigid? And on the one hand, the obvious answer is, oh, RISC-V is very flexible. There's all these things you can do with it. You can add your own extensions, do whatever you want. And this is true. The design of RISC-V was designed in a modular way, so you can easily extend it, add and subtract the pieces you want, don't want, have in your design. So you can really highly tune a core for some application, provided you're prepared to support the software for that core, right? So RISC-V design enables very flexible design point. But RISC-V also enables you to build a very tightly controlled architecture with lots of mandates and very few options. That's also enabled by RISC-V by design. And the way we do this is with the profiles, which put a rigid architecture definition on top of this massive catalog of extensions. Like Krste mentioned, over 100 extensions out there. So if you allowed people arbitrary choice there, that's good when you're building a flexible core. It's not what you want when you're building a core that's going to run tens of thousands of software packages, precompiled software packages. But that's OK. RISC-V supports both these models, right? So it's flexible, and it can be rigid by design. Now, people worrying about RISC-V fragmentation they're really confusing the former with the latter, right? If you want it to be rigid controlled, you can do that. That's what the profiles are for. If you want to be flexible, support the customization for specialized use cases, you can do that too. So fragmentation is not really the challenge here. It's really, we provide this flexibility. It's like some architectures only support the rigid model, and you cannot innovate, you cannot do anything different, right? It's not a weakness of RISC-V that it also supports the flexible one. The strength is both these things can be done, and they can leverage work done for each other, okay? Now let's talk about, now this is, some ways theoretical. This is what the architecture allows you to do. We can write specs day in, day out, but will anybody obey these specs? What's going to actually happen out there in the ecosystem? So I want to talk a little about the dynamics of binary software ecosystems. What I mean by this is software ecosystems where most of the software is going to be distributed as pre-built binaries, right? So Linux distros, Android, etc. So how does this environment going to work? What's the dynamics in this space? Well, the people providing the software, they would like their software to run on as many devices as possible. They spent all this energy building these codes up, supporting these packages. They would like it to run on the widest number of devices possible. And so what they're going to do is look around and see what's the lowest common denominator of all the fleet of devices deployed in the field. That's what I want to target. That'll increase my market, right? Number of devices out there. Now, the other part of the dynamics is the people building the hardware. So people building the hardware, they don't want to spend energy adding new features if nobody's going to use them. So if the software vendors take a look and say, well, only 3 out of 4 companies have this feature, 2 out of 5 have those features, I'll just subset down to what everybody supports. The hardware vendors who invested in building that new feature, if the software is not using it, they're going to say, why did I bother putting this new feature in, right? Maybe I should go down through the subset and not spend all that energy building that new thing in. But the reality is, to be competitive, architectures have to keep adding features over time. So we're working through, new extensions. We basically caught up with other architectures, and now we're doing the same process of, as new things show up, we add new instructions, fill in the gaps. You need more features over time to remain competitive. So what's the real resolution to this puzzle, right? Chicken and egg. Software guys won't use it if nobody has it in the field. Hardware guys won't put it in the field if software is not using it, right? So you have to get an agreement, especially in RISC-V, which is up-and-coming new architecture, amongst everybody, that we are going to move RISC-V forward on a given cadence, on a given roadmap. So that's what the RISC-V profiles were designed to do. They provide a resolution to this dilemma. So the vendors get together and agree on the roadmap over time of when the features are going to get added, what features are going to be in there, making sure everybody implements this mandatory set of features so that in a year or 2 or 3, it takes a while for hardware to come out, software will see in the field all these devices supporting that mandated set of features. And software can then rely on it. And then the RISC-V architecture gets more competitive because you have a richer base on which to write your software. Okay? So this is what profiles are for. This is why they're critical to the acceptance of RISC-V in the application processor space. And again, it's the community coming together and deciding together what is that roadmap of features. We all agree on this, and we all push it through, and all our devices will implement this mandated set of features so software can rely on it, right? And then RISC-V becomes a reliable partner, even though there are many individual companies providing parts. RISC-V community becomes a reliable partner to the software community, providing them a stable, solid, unfragmented device base to port to. So let's talk about RVA, application processor profiles. So RVA profiles were designed to support this rich binary software ecosystems running on application processors. Things like Linux distros and Android, where there's tens of thousands of pieces of code that are precompiled and should just be able to download and run on your hardware, right? One of the goals in RVA that as we release new versions of RVA, it's going to be backwards compatible. So the new versions will run the old binaries. That should be the norm. The other thing to realize with application processors, while all the limelight is taken by the biggest, baddest, highest performance, data center core or biggest, baddest smartphone mobile processor, there's also a demand for lots of other devices that want to run that software, but at the lowest cost. So you'll have everything from the biggest, widest, 8-issue, 10-issue, out-of-order superscaler, all the way down to a 1 or 2-issue core, in-order core, and they all want to have that same set of features to take advantage of this large software ecosystem. So RVA is not only for the highest performance cores, though it will definitely be used there. but it's also for these lower cost cores. Now, one thing I should mention, in the talk I'm talking about RVA, RVA20, RVA23. These have been our internal engineering names we use while developing the profiles. We're working to rebrand these to a more public, external, visible, maybe more appealing name for these profiles when we do the major profile releases. Right? So I'll keep using the RVA names because we haven't quite settled on those external-facing names yet. So we've already ratified a couple of RVA profile specifications. RVA20 was really meant to represent retrospectively capturing what was effectively the de facto standard that we actually set back in 2016. So back in 2016 at the workshop at MIT, we had a bunch of discussions with distros and everybody else and told them, just compile everything for RV64 GC. And that was kind of back in 2016, we decided this. And so the RVA20 is really capturing that, more formally capturing what we actually told people to do back in 2016. RVA22, we also ratified. That's really a significant cleanup, going through the privileged architecture, enumerating all the different actual options that were in there and nailing them down. And also, there's a lot of new extensions that have come along since the original ones in 2019. But now the new one we're working on is called RVA23. And the real key features here, this is a big step forward. It has mandatory vectors, mandatory hypervisor, and high-performance vector crypto as a localized option. Right? So this is quite a big leap up in capability in the profile. So let's just dive in a little bit more about profiles. Maybe not all of you have been following this in depth. So we define a profile. It includes mandates and options. So the profile says, these are the mandatory extensions. Here's a long list. And those must all be present in your device in order for it to be considered compliant with the profile. But we don't only have mandatory extensions, we also have options. And the options come in a few different flavors, depending on the reality of that option. So for example, I mentioned in the previous slide, a localized option. So this is an option that has to be an option because of jurisdictional boundaries, geopolitical issues. For example, the cryptography ciphers, the instructions to support those are options because different ciphers are used in different locations around the world. We're a global standard. We want to support global options, right? So sometimes it's an option because it's only available in one geo or another, right? We also have what we call development options. These are options that are new early in the life cycle, new features we want to add that are not quite ready to be made mandatory. Like we need some more work on them. We want to put them out there. They're ratified. But we want the community to build support for them. And this is part of the roadmap and the life cycle of this extension. It may become a development option before it becomes mandatory. Another class of option are expansion options. And these are things that are very useful, but also tend to have a large cost. And an example might be the matrix extension, attached matrix instructions. I'll talk a bit more about those later. So this is something that not every system will want to have mandated as necessary. And also, it's a case where runtime discovery can handle it. The code for this extension is really well contained within a few libraries. And so you can just detect whether I have this extension or not, and just bring in that code dynamically without having to worry about tens of thousands of binary codes, or including this instruction or not. If it's reasonably well contained within a library, you can use runtime discovery to decide whether you use it or not. And these maybe remain as expansion options for a long time in different profiles. It may never make sense to make them mandatory, right? There may always be an option you add in. The last category is kind of an odd one. It's transitory options. Sometimes we'll add something in, either as a stopgap or to try something out. An example was scalar crypto. We had that in RVA22 because we were not ready with vector crypto. But now we have vector crypto available. We decided that we don't want to continue supporting scalar crypto as an option in the application cores, right? Now, I think to realize with options, all of these are things the software cannot rely on because they're options, right? The mandatory extensions software can rely on and just compile them in without checking whether they exist on the platform. But the options, software has to do some work to figure out if it's present or not and have a backup strategy in case they're not present. That's the nature of an option. So you may be wondering, how can I drop an option and stay backwards compatible? Well, the answer is your software should not have relied on the option anyway. So if you remove something, your software should have a backup plan anyway. So it's OK to drop an option as you move forward in the profiles, but you cannot drop the mandates. Right. Now, another thing with the releases, we talked about having over 100 extensions. Now we have several profiles coming out year by year. And it can be hard to keep track of all of this. And so one of the other big discussions we've been having around profiles is major versus minor releases. Now, this is not settled. We're not definitive yet. But the discussion is trending towards this model, where we will designate some releases as major. And you'll know they're major because they add mandatory functionality. And the reason we'll make a major release is when there's a substantial upgrade in the mandatory functionality. So for example, RVA 23 will become the next major release, most likely, because we've added the vector hypervisor. That's a substantial increase in functionality added to that release. Right? Now, future minor releases, we want to keep having releases. And I think the model we're moving towards is where the future minor releases do not include any new mandates, but only options. And the reason is this allows new software that's compiled to the previous, well, even to this new minor release, will keep working on the old hardware because it has to have treated any new feature as an option and be able to work with or without it, right? And this allows us to help the ecosystem build in support for these new features until we get to a future major release where some of them become mandatory at that point in time, right? So you can imagine the time scale of these. The major release is more defined by the features, having taken a major step forward, whereas the minor release is maybe more of a train leaving the station model of, every so often, maybe every 6 months, every year, we do a minor release that includes newly ratified extensions that are works in progress, right? The idea is the major release will be a slower cadence, like every few years we'll do a major release. When there's something big and significant to add, and the minor releases will sort of fill in the meantime to help provide that roadmap. And again, the whole community should be agreeing on this roadmap. What are the features that we should add to the RVA application class cores over time? Now, one thing I'll also say, this is just talking about profiles, which are instruction set features. There's also platforms, hardware platforms, which is a much bigger set of specifications. So we are making a lot of progress on standard server platform specifications in the server SoC group, and the boot and runtime services group, amongst others. And we're working on this full platform server spec, and that's expected sometime soon. So this is a whole nother level of specification of a whole system, how it boots up, how it runs. And this will be the thing that will provide the meat for the RISC-V certification program that Krste was mentioning. So once these specs are available and hardware platforms are available, we can certify this platform meets the RISC-V platform specifications. Okay. All right, just to change topics a little now, the specifications themselves. So I want to say it's been a tremendous amount of work. I want to thank everybody involved, by the staff and volunteers who've been pulling together all the individual specifications we have into one document tree. This has been the big project, still a work in progress. You can go find it here. And our goal really in doing all this is to bring all the specifications into one tree, and from this repo, we're going to build all the other, render all the content that's needed by humans and machine from those specifications. This is kind of the goal we're working towards. And so we're going to be publishing out of this tree, in various forms, all the work. So we're going to officially version and publish the whole spec. So the privileged architecture, the unprivileged architecture, the profiles, all the other pieces of specifications come out in one tree. They'll be hyperlinked and navigatable so you can find everything easily. It's going to take some time, but that's the vision, and we're making some good progress on that. And I'll say there's a call for help as well, so please work with the documentation SIG on improving this and ideas on structure and other outputs you want to have from this doc tree. All right, so go please check this out right now. It's not quite ready for prime time, but it's definitely reviewable. But please go take a look at this doc as it is right now. Okay, almost last section. I want to talk about RISC-V and AI. So this is a hot topic, has been for a long time. I just want to point out that when we originally developed RISC-V back in 2010, we developed RISC-V in a project all around specialized computing engines. That was the goal research project at the time, and that was before AI became a thing. So AlexNet happened in 2012, roughly. So we were doing this work on specialized stuff before AI hit, maybe fortunately. And then later in RISC-V, when we added vectors, we wanted to make it one of the goals of the vector extension was to make it efficient at mixed precision operations. In fact, a lot of the design is predicated around supporting mixed precision operations well, which is actually very commonly needed in AI. You have small inputs being accumulated in larger accumulators. Now, what's happened is over time is RISC-V was already adopted in lots of AI accelerators. Everybody from NVIDIA using it in their GPUs to Facebook Meta using it in their accelerators. You'll see RISC-V in a lot of AI sockets already. It's effectively like the standard core you would use if you're building an AI accelerator. One of the reasons is the RISC-V flexibility allows you to add those extensions easily to support specialized AI processing. But one of the topics coming up at RISC-V International is, what about standardizing some AI-specific extensions beyond what we already have in the vector instruction set? So, there's a bunch of groups working on RISC-V matrix extensions. Okay, so and there's actually two kinds of matrix extensions being worked on right now. One is the integrated matrix extension, and this uses the vector registers as the input and outputs to the matrix operations. So no new state is added. It just works within the existing vector register state. This is obviously somewhat limited in size, but it's still very useful and reasonably low cost to add these operations. On the other hand, the attached matrix extension adds a lot more state to the processor and consequently allows you to have much, much higher throughput on these matrix operations at the cost of adding a significant size unit to your processor. Right? So RISC-V, we're working on both of these. Now, one of the challenges, I think, here is this space is moving very far and fast, and also matrix operations are different than, say, vector, and it's leading to some discussion in the group, and this is one of the topics I think it'd be good for people to chat in the hallways about, is standardizing the ISA the right thing to do for matrix operations? Or should we just standardize the API? And I'll walk through, some people's knee-jerk reaction is, standard ISA is what I know, that's how I want to do this, but you need to think a bit more deeply about matrix operations and how they work, and where they're used and how they're used. So first thing is, matrix operations only help you on a very small set of high arithmetic intensity kernels, right? There's only a certain set of matrix operations for which this accelerator will give you a big speed up over a vector unit, right? They have to be, doing n-cubed operations on n-squared data. Those kinds of operations, there's only a few of those in practice. Maybe many different data types, but only a few actual kinds of kernels. In reality, when somebody deploys an AI app, they're going to have to deal with a large variety of available hardware support on the cores they're targeting. So going back to expansion options, various kinds of matrix support are going to live in that camp of being expansion options, not always available on every platform that wants to run the same software. You may have no support. You may only have vectors. You may have only IME. You may only have AME, the attached matrix extension. You may have your own custom extension. We're going to see, I'm sure we're going to see about 20 talks on custom AI extensions at the summit this week, right? So there's going to be a great variety in hardware support out there. Another question is, say we standardize a single matrix ISA, how performance portable is any code using that going to really be? Given that, matrix operations run really fast, working well depends on having the memory hierarchy supporting it really well and doing things like tiling in that memory hierarchy. So how can we really build a single ISA binary for matrix ops that's going to run fast on a large number of implementations? And it's kind of a bit of a moot point, but getting back to the earlier point, different machines are going to have or not have the matrix thing, so we're going to have to put an API interface in there anyway and be able to slot in different libraries that do it or not use the matrix thing, right? So like I said, I'm not giving you a value judgment, I just want to see the discussion here, so people are thinking about this when talking about AI in the matrix operations. Also, I'll mention, again, the matrix operations are only a small set in terms of numerically what kinds of operations are done there, like how many different functions you use. The vectors are used for many, many, many more functions. And for there, we do have a standard ISA and a rich existing software programming model to support all those different kinds of functions. And there it is much easier to have much more performance portable vector code. Just matrix operations are harder to make work well across a lot of different systems. Okay, so that's one topic. I want to shift topics a little bit. So RISC-V is also, as well as AI, I don't want to forget about security. So one of the goals in RISC-V is to make it a very secure architecture in parallel with everything else. So we have a bunch of new security extensions in progress. I want to highlight one of them, which is SMTT, or supervisor domains. This is basically RISC-V's way of supporting confidential computing at scale, so providing enclaves, if you like, and other forms of isolated confidential compute. There's a group starting up looking at lightweight memory tagging. This is building on the earlier support for pointer masking, so now providing ways of supporting memory tagging. There's a group looking at cleaner ways of doing this, building upon the experience of the other architectures' attempts to support this. We'd like to do something cleaner and more lighter weight in this space, but provide the same facilities. Cherry is another topic. So Cherry is a capability-based architecture being developed by folks at Cambridge and elsewhere, and now starting to see some commercial cores start to become available in RISC-V, and so there's a group there starting up trying to standardize this Cherry support as well. And finally, shouldn't forget there's additional crypto work on. We're very happy we got the vector crypto. That was the single highest priority a few years back to get the vector crypto done. Now folks are building groups to look at post-quantum crypto and also enhancing existing vector crypto. So a lot of work going on in the security space in RISC-V. So I'm going to wrap up a little early, so I'll leave a few time for questions. So just to summarize, RISC-V, well established and embedded. Nobody gets fired for using RISC-V and embedded these days. It's maturing into a reliable partner for those application processor software ecosystems. It's going to take a little while, but we're getting there. And I think in 5 years' time, you look back and be surprised at how prevalent RISC-V is in those sockets. The specifications are moving towards a single navigatable document tree. We're making a lot of progress on server platforms, also the features in the server platform like RAS, QoS, and security. In AI, RISC-V is already considered the natural starting point for new AI accelerators, and really we have to figure out how best do we intersect RISC-V standards with AI software stacks. Okay, I'll finish there, and I've got a few minutes for questions. So.
Okay, thanks a lot for your very interesting talk. So we have time for a few questions. Are there any questions?
See with the lights. Okay.
There's a question. Please wait. We have a microphone.
Hi, Krste. I'm Atul from Qualcomm. I just have a question on profiles, because we spoke a lot about the RVA profiles, right? Is there a similar effort for microcontroller class, the RVM profiles?
Yeah, so the question was about, are there other profiles? So RVA I focused on, as it's the most important one, the one we're driving things from. There was a request, you should think of RVA as the natural target for a binary software ecosystem. We also developed RVB, which was meant to be sort of cut down a much more flexible profile for systems where you expect to build a custom software stack, so Yocto, open embedded kind of build. So not for binary distributions, but for open embedded Yocto kind of builds. And then there also was interest in a microcontroller profile. So I wrote a thing called RVM23. People go take a look. And there I was trying to understand what do you do in a microcontroller profile. And the goal of the RVM was really to standardize the ISA features. Like in a microcontroller, you're going to have like the bit manip extensions. You're going to have maybe P extension coming later. So defining a reasonably comprehensive set of ISA instructions for microcontrollers so software can simplifies the toolchain's life. Also enables, even in the microcontrollers, you do have binary distribution of things like small code size libraries or codecs or other code bases that will benefit from this. So frankly, there's been less engagement on RVM. I welcome more people to get involved, to actually raise up having RVM. There is a draft to go look at for the RVM, the microcontroller profile, as well as RVB for the kind of Yocto-style builds. Thanks.
Okay, any more questions?
There's one at the back.
There's a question over there.
There's another one over there later.
And over there.
Hi, a comment more than a question because there were no questions. I'll give a little bit more information on whether we standardize on an ISA or an API for the matrix operations. That's already been done. So C++26 does have mandated API in the standard library for some matrix operations with more linear algebra operations to come, because you have this wide range of implementations behind. So a library, in my opinion, is a good place for that. And the C++ Standards Committee also think that. So that might be a good place also to start interacting. I have much more of a RISC-V presence and drive on the C++ 20 or C++ post 26 environment as well.
Yeah, I'll just say there's many library APIs. That's not the issue. It's like picking the right interface to people's environments and how they pick things up when they're not writing in C++, and they're writing a different language. So it's a bit broader than that. That's good to have an effort there. You should bind into that. But and the other problem is instruction set. Getting agreement on instruction sets is really difficult. Getting agreement on APIs is pretty much impossible. So we're going to have to figure out how to, cross that bridge. Right? There's many more cooks in the kitchen when we talk about API versus instruction sets. Yeah.
Agreed. And that's sort of the point of putting it into a language definition, right? Is that as soon as a language makes it concrete, it becomes a de facto standard across more than just that language. If a compiler has to support it, then every API starts looking like something what the compiler already understands.
Okay. All right. There's a question over there.
Yes, there was one more question. Would suggest that this is the last question then. It was there at the back. Yep.
Thank you. I have two questions. The first one is that because now we are in Munich, so do you expect we would have automotive extensions, and also we can put, expect the RISC-V Foundation have more attention on automotive segments? Expect RISC-V can have exploding segment in automotive. The second question is that we see a lot of progress on the high performance or application processor for whatever AP or server, and also we see the progress on AI. Besides these two segments, what's our expectations, for RISC-V to have more deployment or have more market share? I think all the technical folks or investment will, have more return on the markets, right? So I think this is my two questions. Thank you.
Okay, I think I took the first part of the question as what is RISC-V International doing about various segments, including automotive, for example. I think some of the members, there is some SIGs in some of those areas. A lot of the different segments, some of the requirements are more at the platform level than the instruction set level. And so I think some of the vendors in those spaces have solutions that add more features at the platform level for some of those areas. It's not so much instructions in some of those segments. So that's really for the vendors in those areas to go figure out the market needs there. In terms of market share, I think the projections that Krste had, those are coming from independent analysis, looking at the opportunities for RISC-V in different segments. One thing I'll say is, for RISC-V, there's no one, this is the clear socket that RISC-V is going for, and everybody should go rush and build RISC-V cores for, Tamagotchi or something. There's no single thing that's the RISC-V, targets. RISC-V is everywhere. It's every space. There's opportunity for RISC-V. Which ones are more profitable? I think the vendors are all running around trying to figure this out. There's both the brownfield replacing other architectures in existing use cases and sockets, and then there's the more greenfield, like a lot of the AI use cases where there's new stuff happening. For example, in automotive, a lot of the folks are switching over. They're designing a new platform because they have to, because of electrification and ADAS. They're moving to a new compute platform, looking to the future. That's a big opportunity for RISC-V. AI is obviously another big space as well. So I think so to be clear, I think there's work at RISC-V International to help on the platform specs for some of those segments. Some of the segments may need some additional instruction set support. I think that's less of a thing. It's more of a platform level usually. Once we got past, filling out most of the gaps that we have right now. And the vendors are really the ones who will figure out the market opportunities. I think RISC-V International, we're a standards body. We want to promote the whole space, but we track where the opportunities are, but it's not really our job to ferret out the market sizes in those spaces. The analysts could do that, and the vendors could do that. Thanks.
Okay.
Okay,
Thanks a lot. Let's thank Krste again for the call.